take this one battery circuit analysis problem where you have to find everything through each resistor, the current, the voltage, and the power dissipated. How would one approach such a problem? We can use the method of tree analysis and apply Ohm's law to each tree element. Let's recall what Ohm's law is. You can recall this using the following mnemonic device. V equals IR, I equals V over R, R equals V over I. Now the power dissipated in a circuit is given by the formula P dis equals voltage times current, or I squared R if you want to get rid of the current of the voltage using Ohm's law, or if you want to get rid of the current, you can write it as V squared upon R. Now we're going to use the following conventions in our circuit analysis. We're going to indicate the voltage by the triangle symbol V, and the voltage is going to be in volts on all of them. Because the resistance is in kilo ohms, we can expect the current to be in milliamperes, the power dissipated to be in milliwatts, and the resistances themselves will write simply as numbers. It's understood that if you write them as numbers, the resistances are in kilo ohms. Having this sort of convention keeps us from worrying about units and focus on the circuit analysis instead. So how do you reduce the complexity of this circuit? Well, first of all, let me draw the circuits here. I'll start with the positive side of the battery. I'll move it up to the top, and then I encounter R1 and R2 to the left, R3 and R4 to the right. So I'll mimic that as the branches of the tree. That's 1 and 2, 3 and 4. The branches then meet up and then go to the negative terminal, which are the roots of the tree. So that's your tree diagram. Now this circuit is sufficiently simple that I can do two at a time. So I'm going to combine these two in series and those two in series in the next step. So I'll be getting the following diagram. Resistances in series simply add. So let's recall what that formula looks like. It's R1 plus R2. And resistances in parallel add harmonically. So that's R1 R2 over R1 plus R2. One and 2 gives me 3. 3 and 4 gives me 7. And the last stage on this tree would be to combine 7 and 3 in parallel. So that gives me 7 times 3 over 7 plus 3. And that's going to be 21 over 10. And I will write that as a fraction. Notice that this is essentially your effective resistance. So the last step in circuit reduction is always the effective resistance. I'm going to label these trees now as 1, 2, and 3 and analyze them in reverse order. That's the simplest circuit, so that can be used to find the current in the circuit. So let me start like that. The current is equal to the voltage divided by the resistance. So that's going to be 100 over 21. And the value is going to be in milliamperes. Now, rather than approximate with decimals, which can be pretty troublesome because at the end you may not have agreement. Also, each rounding will reduce the accuracy of subsequent steps even for things like voltages. I'll keep the fractions as long as they're manageable. If they get out of hand, then I can quit always. So let's go to the second tree and see what we can get from that. The total current cannot be just written like that. You have to split it properly. However, I can write the total voltage immediately. Voltages across parallel elements are always the same. So I can write the total voltages immediately. For the current, here's what I do. I try to find the current through I3 and see what I get. By Ohm's law, that's V over R. 10 over 3, and that's the current through that branch. If you have 10 over 3 through that branch, then the remaining current, which is 100 over 21 minus 10 over 3, must go to the other branch. That 21 makes me think that maybe I should write this as 70 over 21, multiplying both the numerator and denominator by 7. And so the balance is just 30. 100 minus 70 is 30. So I can write my currents now. Okay, now once I have this, I can go to the first step. Now the currents through a series arrangement are going to be the same. So this has the same current through both of them. So I can continue writing 30 over 21 and 30 over 21 for that. And for these, I'll have 70 over 21 and 70 over 21. What's not clear is how the voltage splits up. How does this 10 volts split up? Well, there too, what you have to do is realize that a bigger resistance always grabs the bigger voltage. But there's no guesswork involved. Let's just use V1 equals I1R1 for this one. The current is 70 over 21 and the resistance is 1, so that's 70 over 21 volts. V2 is going to be 10 minus that, but I'm too lazy to do fractions, so I'll calculate V2 directly. The current through V2 is also, through R2 is also 70 over 21, and it's going to be times 2 this time. So that's going to be 140 over 21. Let's just make sure they add up to 10. 140 plus 70 is indeed 210, and 210 over 21 is 10. So that makes sense. Similarly, I'm going to find V3 and V4 next. V3 is 30 21st times 3, which is 90 21st. And I don't want to deal with fractions, so I'll calculate V4 from scratch. That's 30 21 times 4, which is 120 21ths. A quick reality check. 120 plus 90 is again 210, and 210 divided by 21 is 10. So everything works out. Let me put the voltages there. And so we have essentially solved the problem except for power dissipated. For power dissipated, I'm going to use the formula P_dis equals V times I. Well, in our diagrammatic language, that amounts to triangle times circle. So wherever you see a triangle and wherever you see a circle, just grab them and multiply them together. Unfortunately, everything is in fractional form, so I can expect some minor headaches here. That shouldn't be too bothersome, I think. Let's see. Let's find out. So circle here is 121, triangle is 10. So I'm going to get 1021. What do I have here? Oh boy. 90 times 30 is 2700. So I'm pretending not to freak out here. So that's 2700 over 21 squared, because I have 21 and 21. And here 70 times 70 is 4900 over 21 squared. All right. Now 70 times 70 is 4900, but 70 times 140 is 4900 times 2. Okay, so that's 9800 over 21 squared. And lastly, I have 30 times 120. 12 times 3 is 36. So that's going to be 3600 over 21 squared. So in principle, I have analyzed the circuit. Now, the acid test is the hope that when I add these fractions, which look very weird to me, I will get 1000 over 21. So is 1000 over 21 the same or not of 4900 plus 2700 plus 9800 plus 3600 divided by 21 squared. So best way to do this addition is I don't have a calculator, so I'll just add them like this. Eight, 6, 14 plus 9, 23 plus 7, 30. 9 plus 3, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Oh, it's almost hard to believe. That's 21,000. So 21,000 divided by 21 squared is indeed 1000 over 21. Hooray! I was almost ready to start the video over with better numbers, but it worked out. It's a miracle. That's your basic circuit analysis problem. Not very different from your homework problem. Your homework problem is probably a little bit crazier with the numbers.